Today's session is titled, How Much Liquid Does My Sucker Rod Pump? So Lynn, I'll go ahead and turn it over to you now.
Thank you, Carrie Ann. And Gustavo, thanks for watching the questions and keeping track of that. So this presentation is about a question we often receive from the customer. And the customer usually says, the sucker rod program software calculates more than I'm getting in the tank. How come? And so this is the presentation that's going to go through and discuss that. There's a couple of references that we have that you'll be able to download. We wrote a paper back in 2012 on the pump slippage equation that was developed at Texas Tech between 2000 and 2007. And then we recently, in 2015, presented a paper on a thing we call the equivalent gas-free pump fillage line. So we draw a line on the pump card showing how much of the pump displacement is gas and how much is actually liquid. And then we'll talk a little bit about the Q-Rod program that uses the pump clearances and other parameters to calculate the slippage and allows you to design your pump clearances and actually plan on the amount of slippage that you'll have when you run your pump in the well. And then this last reference here, there's a couple of spreadsheets that are provided. One spreadsheet is a slippage calculator using the slippage equation, and it's called the Patterson slippage equation. And then we will also have an Excel spreadsheet called the slippage viscosity calculator, because the viscosity of the fluids between the plunger and the barrel also are important. So anyway, this is our talk on this. So this is a actual surface card and pump card, and the pump card has incomplete pump fillage, and so this shape right here means that part of the downhole stroke of the pump, this portion of the stroke is being lost to gas compression, and we call that gas interference. And so when we look at this shape, the pump, then this means that there's gas being compressed. And so when you look at the pump card, we calculate typically in TWM, and in one place in TAM will show that these number of inches right here of equivalent pump travel, this is called the effective plunger travel line, that then is used to calculate a pump displacement if the pump was completely filled with liquid from the pump stroke from here down to there. That much liquid, 74 barrels per day, would be displaced up the tubing. And so there's not just liquid inside the pump. And some of the liquid that's in the pump came from above the plunger from the tubing by slipping between the plunger and the barrel. And so this is in TAM, we're going to go show you the idea of replay. And so you click on the replay button and you can set the replay to loop. And so here we're setting it to loop, and we're going to show strokes 1 through 7. And we have gone through, and this pump card is called the gas interference pump card. And so this again is incomplete pump fluid, the gas interference. And you can see this blue line represents the line where would be gas above this amount of gas in the pump and this amount of liquid plus slippage below this line. And so when you see this pump card on the details tab, it shows an adjusted pump displacement, which has been adjusted for several adjustments. And we might note that the pump stroke here is shorter than the surface stroke. That's due to the stretch of the rods, picking up the fluid load. And we sometimes people say, well, just take 80% of the surface stroke and that's your pump displacement. Well, that doesn't work very well either. So you can see over here the animation on the right-hand side, and the animation shows that there are green bubbles which represent oil and white bubbles that represent gas, and the blue represents water. And so we'll go through a couple more animation steps here and talk about that just a little bit. So here the trailing valve is opened, and that corresponds to this point right here on the pump card where where the trailing valve opens due to having the pressure inside the pump chamber pressure greater than the discharge pressure above the plunger. And now we're lifting fluid with a closed trailing valve. At that point, the trailing valve closes, and you can see the well fluids enter the pump chamber. And the ratio of these fluids are supposed to be proportional to the pressure. And so the pressure here at this point is intake pressure. And then as the plunger moves down, the dots get smaller, the white dots get smaller. And at that point, the little dots represent the volume of gas that's still inside the pump chamber. That represents this distance from here to here. We call it the equivalent gas rate pump fillage line. And a lot of these calculations are adjusted based on this button right here called pump card analysis. So when you look in TAM at the field view, we show two pump displacements on this screen. And if you select more than one stroke with the events button, it's going to be the average of those strokes. But in this case, we just are showing one stroke, stroke number 7. And stroke number 7, if you have this much of the stroke all the way for the maximum plunger travel, and if the pump were completely filled with liquid on the downstroke, then this liquid displaced in the tubing would be equal to the inches of stroke input to that equation times this pumping speed times the diameter squared times a constant would be the pump displacement, and that's approximately 800 barrels a day. Well, that's not true. And so this compression curve shows of gas shows that the trailing valve opens right there, and if the pump were completely filled with liquid, then the pump would displace at this point from here to here, the effective plunger travel filled with liquid, then that stroke, assuming all liquid, no slippage, will be 344 barrels per day. And so this example here called gas interference will be one of those files that you can look at, and we'll talk about this some later during after questions and answers. So actually what we have on the details tab is something that's now different than these two pump displacements on the field view. These are assuming all liquid inside the pump. And here on the field details view, we have gone through some adjustments. And we're adjusting the pump displacement now, the effective plunger travel based on free gas that's in the pump at the discharge pressure, the volume, which takes up this many inches of stroke, and also the slippage. And now this could be gas expansion or it could be slippage. And so we lose part of the stroke due to slippage because there's slippage required to keep the plunger from sticking and to lubricate the plunger during the stroke. And so you have to have some, but if you have a large clearance, it can be a lot of slippage based on the discharge pressure and the clearance. And so when we click on this pump card analysis button, we have the options inside this software to go through and adjust for unanchored tubing and adjust for, and it uses whether you anchored your tubing or not based on your input, and adjust for the gas that's free inside the pump, this distance right here, and adjust for the delay closing of the trailing valve. So if the trailing valve doesn't close at the bottom of the stroke, then that's also lost stroke. And then also adjust for runtime. If your pump doesn't run, if you have a timer or pump off controller, then this assumes 24 hours a day. And if you check this box and enter the runtime, then it's going to make an adjustment. Say if you run 12 hours, that's half a day to cut this volume in half. Now, the last thing we can do if you want, you can also select an option where the liquid that the pump displacement calculation calculate is the liquid at discharge and intake. It's adjusting the liquid. The gas is in solution based on intake pressure, and we'll talk about that a little bit. But the liquid volume has to go from reservoir temperature down to stock tank conditions, which are default, I think are default in the software to 14.7 psi absolute pressure and probably 60 degrees Fahrenheit. But I don't remember whether it's 60 or 70, but it's on the conditions tab in TAM. Now, so that's kind of an introduction to the idea of pump displacement, and that's what we're going to talk about throughout this presentation. And when we do the calculation, we just do it for one stroke. And so if you select a stroke, then that's the stroke that we calculate, and that's the stroke that's reported on the report. And if you turn to another stroke and it has a different opening of the trailing valve, then it's going to have a different adjusted pump displacement. Now, we use the deviation survey, we use the wellbore information, and we use the artificial lift, plunger size, plunger length, and all those different parameters, the rod string length, the rod string sizes, all those are used. So it's important to have the information about your wellbore and your lift equipment input into the software. Another thing that we use that we don't really, we calculate the oil and water rate based on the pump displacement, but we need to know the percent oil for a stroke. And so if you don't put in the oil and water rate, then we're going to assume a certain percent oil. The water and the oil gravity are used to determine the discharge pressure, and properties. The oil gravity is used to determine things like oil solubility at temperature. So the gravities are important to be entered into the software. Now the gas gravity comes from a floatable shot, if you shoot a floatable, or basically that's where it comes from. And I'm not sure if we default it probably to 0.7 if there's not a floatable shot. The valve opening and closing points of the pump are automatically selected, and they should be at the corners of the pump card, and you should show them, because if they're not positioned properly, the program's going to use those incorrectly located valve open and close points. There are annotations. You should turn the annotations for valve open and close points on if you want to do this calculation, because you need to have the valve open and close points located properly, and we're still working on getting that down exactly correct. And so, if the computer doesn't pick it right, you got to pick it right. Now, the tubing pressure and the tubing fluid gradient and the deviation survey all are used to calculate the pump discharge pressure. And the pump discharge pressure is important because that's what the pressure is when the trailing valve opens. So we need to know that value, and we need to know it fairly accurately. But if you don't have the wrong tubing fluid gradient, or the deviation survey is not entered in the software, or the tubing pressure is left to a default value, then the calculation is going to be off by a little bit. One of the things that we assume during the gas compression is that the free gas that's in the pump with the liquid doesn't go into solution. Now, it can if the oil and gas are in contact, and it's shaken and the gas is compressed, then the gas can freely go into the oil based on the pressure. But we've got a problem in the sucker rod pump, is there's water, and often the oil and the gas are separate. So it's difficult to push the gas into the oil if the gas and the oil aren't in contact. We also assume that for thermal calculations that all these compression behaviors happen at the temperature at the pump, and so we assume it's we call isothermal. There's no heating of the gas that causes the fluids to change, and if the gas heats up during compression, then the gas temperatures is quickly stabilized back to the temperature of the earth. Now, the gas that goes into the pump at the intake pressure is a large volume because it's low pressure, and then it's compressed to a small volume at the discharge pressure when the trailing valve opens, and we assume that the same molecules of gas are present both at the intake and the discharge. So there could be some gas going into and out of solution that would change that calculation a little bit. Now, if you don't type in the oil and water production rate, we're going to assume that there's 10% oil. We use the strokes per minute for that stroke, the pumping speed, and the plunger diameter to calculate the barrels per day. So each stroke is independent in terms of stroke length, effective stroke length, and strokes per minute and plunger travel. So the other stroke won't have an impact on the calculated adjusted pump displacement. Now, this idea has been around for a long time, probably before W. Gilbert published a paper in 1936 where he said, "I built, as Shell oil built, and have always been pretty innovative. they built a downhole load cell that could be run in the rod string. This was a rod string, and it's mechanical. And they would attach a flattened brass sheet of metal, and the tool would rotate, and the load and the position of the pump card would get scratched on this brass plate for each stroke, and then Gilbert would pull it out of the well and have a certain condition. And as part of this paper that was published in 1936, he explained how you'd calculate how much liquid and how much gas are inside the pump. And so this idea has been around for a long time, and I didn't do it exactly the same way Gilbert did, but a lot of people have done this. So there's Jim Lee and Sandia and Tulsa University Artificial Projects, and Gibbs and Nolan published, and other people have published calculations similar to what Gilbert published. And so it's been around for a long time. Now, this is kind of the idea of what we're talking about. If you look at this pump card, and this is the pump card in our examples, and we've got these valve open and close points positioned at the corners of the pump card, and so this is where the trailing valve opens, okay, and we're at the discharge pressure inside the pump chamber. So when this trailing ball comes off the seat, the pressure inside the pump chamber has been increased from right here. It's at the intake pressure. So when the plunger is moving up, the standing valve, this is where the plunger moves up right here, and liquid and gas are in the pump chamber. And at the top of the stroke, the standing valve ball goes on the seat, and the pump becomes a compressor. And so this says the pump acts as a compressor. It's probably the compressor on your release that has the highest compression ratio. Suck rod pumps, when there's any liquid in the pump above the bottom of the plunger travel, can have what we call an infinite compression ratio, because the liquid allows the gas in the pump to be compressed to extremely high pressure. So anyway, we go from the intake pressure right here, which is created by the pump filling up with liquid during the upstroke. And we can tell that by the pump card load line matching up with the pump intake pressure load line from the fluid level shot. So that those two load lines match up, which means the discharge pressure and the pump intake pressure are reasonably in agreement. And so we start at the intake pressure, the plunger moves down, this is moving down, and the pressure at the intake pressure goes up to the discharge pressure, and that causes the trailing valve to open at that point. And then any liquid and gas inside the pump chamber are then discharged in the tubing during the downstroke. So we intake on the upstroke through the intake valve on the upstroke, and we discharge the discharge valve, which is the trailing valve, on the downstroke. All right, now this slide came from a reference that was from Tulsa University Artificial Lift Projects. It was a study done in 1995 by Hatun Taberski, and it's what it shows is this is the oil gravity here along this axis, and this is the time in seconds for all the gas inside a pressure cell to go back in solution. And so what University of Tulsa did, they would fill a cylinder with a certain amount of oil and gas at high pressure, and then they would shake it until all of the gas was in solution, and they would time it. And so what this is telling us is that what's it telling us? It's telling us that if you have a 40 API gravity oil, it takes about 8 seconds for all the gas to go in solution if the oil and water are in contact. And so at the discharge pressure, the oil and gas are in contact maybe for less than a second. So not very much gas, based on this curve, can go in solution. If your oil gravity is less, then even it takes a longer time for the gas to go in solution. Now, if the oil gravity is light, then it's pretty quick. But even there, here at 60 degree API gravity, it takes at least 4 or 5 seconds for the gas to go in solution if the oil and gas are in contact at the discharge pressure and shaken. So it's unlikely that the gas all goes in solution based on this graph. All right, now, so when you start to do this calculation, step one would be to go into the software and turn on the annotation that says show valve open and close points, because you need to look at the pump card and make sure these 4 points are located at the proper positions at the corners. So this corner would be trailing valve open. This upper left-hand corner would be standing valve open. This upper right corner would be standing valve closed, and this lower right corner would be trailing valve open. And you can grab the little round circle with your mouse and drag it to the right place. All right, so this is a diagnostic pump card shape, and this diagnostic pump card shape is one that we call gas interference. And what we see is that this line right here is flat generally during the upstroke when the standing valve is pulling fluids into the pump chamber. And the flat typically means that the discharge pressure and the intake pressure acting across the plunger are fairly constant. And when we say that this load line should be flat, we're meaning that the dampening being taken out of along the rod string as a function of velocity damping factor is correct, and the discharge and intake pressure aren't changing, and you see your pump card typically have this flat load line, and that's what that flat load line means. And it also means that our standing valve is open. So when you see this flat load line on your upstroke, your trailing valve is closed and your standing valve is open. That's what this note says right here. Now on the downstroke, we see the same thing. Notice it's flat right there. And that means that and this is from trailing valve open to trailing valve closed. That's from point D to point A. And the trailing valve is open because we've got to the discharge pressure, and now there's no pressure differential, very small amount of pressure acting across the plunger, and that load line is typically flat. So you should think when you see a pump card that's flat like this and flat like this on the upstroke, that first of all, this means the trailing valve is carrying a load and it's fairly constant, and this means there's very little load on the trailing valve and it's constant. And so that's what those two load lines mean. And when I see this, I say that means that we have pump action. That transfer of the load between the trailing valve and the standing valve is typically why I'd say there is pump action as well, or there's no pump action if they were both together. So when these two lines are together, then there's no pump action. All right, so the next step. The next step is to come up with the tubing fluid gradient. And the easy calculation is based on the oil and water that are entered into the software, along with the oil and water gravities. We can calculate a gas-free tubing fluid gradient. But if the pump card shows gas interference, then it's almost certain that the tubing fluid gradient will be less than this, unless we have some other kind of issues about viscosity, which is probably unlikely. Now, another thing that we can do is we can do a valve test, and if the valve test is the load cell, then we can very accurately weigh the weight of rods and fluid, and then we can calculate the tubing fluid gradient based on the weight of rods and fluid. But that assumes there's no mechanical friction acting on the rods, and any little change in mechanical friction will make this off. Then we've added this multi-phase flow gradient, which is a shell method with Ross Gray method for gassy wells, and this one works really well for high percents oil, but doesn't work very good for high water cuts. So this one probably needs some more research for typical suck rod wells that have high water cuts. So usually I can't use this method. And then the last method is user entered, and often you have to type in a gradient that's just a little bit less than this one right here because you have some free gas going up the tubing. And so often we'll type in the gradient. It's going to almost always, unless there's no gas being produced or very little gas, it's going to be lighter than that. And this also has a force that we added to TAM that is a mechanical piston force acting on the polish rod based on the tubing pressure. And so you can turn that on or off if you want. So now that we have the true vertical pump depth and the tubing fluid gradient, we can calculate the weight of the tubing fluid down to the pump, and we can add on the tubing pressure, and then this becomes our discharge pressure from our pump card. And so we now have the discharge pressure acting on the pump, and we know a point for the compression. That's when the trailing valve opens. Now, when you collect a lot of data, all the cards aren't exactly the same. And so if you're wanting to try to calculate the liquid in the tank, you probably need to determine a representative stroke. And so it's sort of up to you to decide which stroke you're going to pick. And one of the features that Field View and TAM does, you can show all the strokes with this events viewer and then select all the strokes and overlay them, or select all the strokes that look similar and overlay them, as long as you hold down the control and tap on the screen, or do a click on the first one, hold down the shift and click on the last one. That overlays all these strokes, and then the software says average effective plunger travel. And so then if I was going to pick a stroke for all these strokes to the calculations on, I would try to find a stroke with the trailing valve opened when the effective plunger travel was about 37.77 inches. And that would be the stroke that I would claim that would be the representative stroke. And so in this case, I said stroke 104 is closest to the average, and that's 37.9 inches, and so that's the stroke I'm going to use to do the rest of these calculations in this software. All right, so here we've gone to stroke number 104, and we are on the tab that says pump intake pressure. And the pump intake pressure tab allows you to identify the pump card load on the upstroke and the pump card load on the downstroke, and we'll go through that in an example later on. And it takes the height of the pump card based on FO up minus FO down. That becomes a fluid load, and then it calculates the intake pressure. So we use this pump card height and the FO up line, FO down line to calculate the pump intake pressure. So this gas compression calculation is based on discharge pressure, intake pressure here, which we're trying to calculate on this screen, and discharge pressure right there. So the tubing pressure plus the tubercle pump depth times the tubing fluid gradients to discharge pressure, and you subtract off the height of the pump card and fluid load divided by the areas of differential pressure acting across the pump card, and that becomes the pump intake pressure. And so for this well, the pump intake pressure with this line and that line, and these are defaults, and you can move them if you want. And those this becomes the pump intake pressure that will be used for the calculation from the intake pressure to discharge pressure. Now, here is a slide that shows the equation that we're using, and the equation is fairly simple. All it says is the pressure and volume of the free gas at the pump intake pressure divided by the Z factor, and that's this condition right here. So here's our intake volume and our intake pressure and our Z factor at the intake. That ratio is equal to when you then compress your fluid to a higher pressure right there and a smaller, well, not that volume, but a smaller volume right here, and divide it by the Z factor. Now what I mean, what do I mean? Okay, look, there's some liquid inside the pump chamber, and there's some amount of gas, and the amount of gas is more than this distance right here. So we have an equation that we can develop that says here's the amount of liquid, and we're going to solve for the amount of liquid inside the pump to make this equation be true. And so we calculate this free gas in the pump based on these two conditions, knowing the intake pressure and the discharge pressure and the Z factors at those conditions. We calculate the volume, which is the volume is this distance here times the area of the plunger. So we calculate that at this condition at the intake pressure and the same condition right there, distance, at the discharge pressure. And that gives us this amount of free gas inside the pump. And then we can calculate the liquid. All right. So here's our compression curve, and we've got 36 inches about of liquid, and that liquid's both slippage and it is also liquid that came in through the intake during the upstroke. And it's been compressed to the discharge pressure, and this is the gas right here that we've compressed. Now, when you look at this, you start to think about compression ratios. The compressed gas volume has been compressed 15.8 times from the intake pressure to the discharge pressure. So that's the ratio. This pressure divided by that is termed the compression ratio. And when you compress, so in this well, 79 barrels equivalent of gas, free gas, entered the pump and interfered with the liquid filling the pump. So this distance from here to here is 41.35 inches, and that's equivalent to 79 barrels per day of lost production per day. So this means that the gas separator is acting poorly if there's one in the well. It's not very efficient. And the gas compression is going from 41.35 inches down to 2.77 inches. And when the drilling valve opens at this point, we're still losing 5 barrels of displacement due to the free gas inside the pump chamber. So that's the example of compressing from 41.35 inches down to 2.77 inches with a 15.8 compression ratio, and we're losing 79 barrels per day of liquid production because the gas is interfering with our liquid entering the pump. And this just shows the same thing. It's showing again that this distance right here is the gas volume at the discharge pressure, and this distance from here to here is the gas volume inside the pump chamber at the intake volume. We have the same number of molecules, but it's just compressed, smaller volume because it's a higher pressure. All right, now the slippage. There's an Excel spreadsheet that does the calculations if you want to just use the spreadsheet. It's also in QROD, and the calculation, this equation is also in TAM. And so the slippage, this is a slippage during a stroke. It means the slippage increases, total volume of slippage goes up as you pump faster. Now the efficiency of the pump improves as you pump faster because of the viscosities, the turbulent seal between the plunger and the barrel. The slippage increases as the diameter increases. The slippage increases as the differential pressure across the pump increases. And the slippage increases quite a bit based on the clearance between the plunger OD subtracted from the barrel ID with the power. And the slippage decreases as the plunger length gets longer. And the slippage decreases also as the viscosity increases. Now, when we did the testing at Texas Tech from 2000 to 2007, we had water, and we had water at a certain temperature. So we used in all the calculations of viscosity a default of 0.76. And that's what the default viscosity in TAM is and QROD are. But you can change it based on this spreadsheet. There's a spreadsheet that I provided. So it should be based on the average pressure across the pump and the oil and water and the temperature. We'll talk about that some more. So look, when the pressure above here is high and the pressure below plunger is low, and there's a force that's applied to the fluid that causes the fluid to slip, to travel from above the plunger to below when the trailing valve is on the seat. So when the trailing valve is on the seat, then fluid is slipping back into the pump chamber due to this equation that we have, and it's a good representation of the slippage for a stroke. Now, so after we finished this slippage project, my involvement was driving back and forth between Wichita Falls and taking 3 Echometer well analyzers, and every time we did a test, measure surface data and pump intake pressures and power, and through a micromotion flow meter, the instantaneous flow rate. So that's what I did. That's what I provided, and I worked with John Patterson and Kyle Chambliss. He works for Oxy now, but he got his PhD on the project. And so at the end of the project, we wrote a paper, and we can send you this paper if you're interested in it. That sort of outlined what we did during the slippage test. And one of the things that we said was that, and now I said we should use the slippage equation, and John Patterson and Jim Curfew said, no, we need to put a table inside the paper that says if you have a certain diameter pump, use this kind of pump clearance. And so we argued and voted, and Kyle wouldn't vote, so I voted against the table, and John and Jim voted for it. And their reasoning was that when you have solids, you need to have open pump clearances. And my opposition was when you don't design the clearance and you have too much open clearance, that you're going to have a lot more slippage than you expect. And so that's the paper that this group published. And then in 2012, I published a separate paper that said, don't do this, use the slippage equation. So you're welcome to read both of them if you'd like. So here's the results, and this is basically why I wrote the paper in 2012, that if you use that table, and here's the calculations, and you can put in a spreadsheet and repeat them. Here's the pump clearances, and so here it says if you use a 2 1/4 pump with 9 thousandths clearance, you'll have a pump displacement of 211 barrels per day, where you'll lose 79% of your pump displacement to slippage. So can you imagine going into your boss's office and saying, hey boss, I just ran this brand new pump, I did a great job, and I designed the sucker rod pump clearance based on this paper was published by Echometer in 2007, this paper right here. And it says that we are only supposed to get 21% of our new pump displacement. And I think that would be terrible. So that's kind of why I wrote the paper and said use the equation, design your displacement for your conditions in your well, and include your slippage in your calculations. All right, so here's an example of some data we collected. This is the pumping speed right here, speed here versus slippage. You can see as you pump faster, you get more barrels per day. Slippage for different size pump clearances. This is 7 6-rod strings, which is 7/8, 3/4, and 7/8, and then 6 3/4-inch rods. This was a 1-inch rod string, and the 1-inch rod strings were stiffer. And so we had 2-inch plungers with 9 thousandths clearance, 1.5-inch plunger with 1 and 5 thousandths clearance. And all these show that as you pump faster, the slippage would increase with pump speeds because there's more strokes. And then this is adjustment for viscosity of 0.76. And this is the plot that shows that the efficiency improves as you pump faster. And that's because of the turbulence between the plunger and the barrel during the upstroke that makes it more difficult for slippage to occur at high speed. So it says efficiency is the best as you pump faster. If you have 5 thousandths clearance or 9 thousandths clearance, you pump really slow, like 1 stroke per minute, then almost all of your liquid is going to be lost due to slippage. So you have to be cautious about running open clearances if you plan to pump very slow with a variable speed drive or some kind of jack shaft. Then you probably need to watch out and really pay attention to your pump clearance. All right, so this is inside the TAM software, and it's showing that you need to make sure that you enter your plunger length, your plunger diameter, and your pump clearances. If you don't enter those in, then your calculations will be defaulted, and we'll assume a 4-foot plunger, and we'll assume 3 thousandths pump clearances. And so those both are very much impact the calculations. So the clearances to power and the length would result in reduction by using 60 inches versus a 4-foot 48-inch plunger. Now the viscosity is a lot more complicated than just 0.76. So initially we use 0.76 as a default, and this is the output from the spreadsheet, and you can get it from the Ask Echometer webpage. And this is the intake pressure, and there's the discharge pressure for example well. And you can see here that the viscosity changes from 3 down to 1.8 of the oil, and the water viscosity is right here, and it's basically much less than 0.76 because it's hot. And so the combination of the oil and the water viscosities often result in an average viscosity almost equal to a 0.76. So the default number probably is okay, but basically you can make a better estimate of viscosity by using that spreadsheet, and eventually we'll get it programmed into TAM, and you can select it as an option. And so here it's showing the output of the spreadsheet. It says here we've got this amount of oil, this amount of water. Here's our pump intake pressure. Here's our pump discharge pressure, and the average viscosity would be 0.25 if you use only oil, and the average viscosity of the total fluid is, it'd be 0.36 is based on the water, and the average viscosity is, let's see, total fluid. There's total fluid. So this well makes a lot of water, not much oil, so the viscosity should be controlled by the water. Now, what we found out was that it's a little more complicated than that. If you have your oil, if your oil aperiodic gravity is less than 32, then the oil viscosity dominates the viscosity. So this is what dominates the viscosity when you have a heavier, more viscous oil. But when you're greater than 30 to 32, then the average is best, or that 0.76 usually works pretty well. So in this well, we probably would use this number, because in this well, the oil gravity is input is going to be less than 32. So this is the calculations inside the software that we talked about you needed to make. And so here's the maximum plunger travel in this well, different well. Here's the amount of free gas at the pump intake of inches. Here's the effective plunger stroke. Here's the free gas at the discharge compressed to a small distance. Here's the slippage based on the pump clearances. And then we've calculated, using a fluid viscosity of 2.53, a good match based on what's actually produced to the well. If we use a viscosity of 2.539, but it doesn't match if we use a lot higher, a lot more slippage, if you use the 0.76 viscosity. So this is an example of a well that higher viscosity is required to get a good match. All right, so this kind of talks about viscosity. It says that it's a good guess for most cases, and that's what we've seen. Use only the oil viscosity when you're less than 30 to 32. Use the total fluid viscosity when you're greater than 30 to 32 API gravity. Use the average pressure. Use the temperature of the pump intake. You need to know the plunger length, diameter, and clearances. You need to know the gravities. And you probably should set the bubble point pressure equal to the pump intake pressure, because the bubble point pressure in this Excel spreadsheet is used to determine how much gas is going to go into solution at the pump. So use the bubble point pressure as a pump intake pressure. This is the Pattersons slippage equation. So this one shows that we have 11 barrels per day of slippage. That's at 5.6 inches to reduce the pump capacity. Equals a certain number of barrels per day, which is what happens to be 11 in this case, or 11 barrels of slippage. So this is the table that shows the inside of TAN. It shows that the total maximum plunger travel is 77 inches. You have 41 inches of free gas at the pump intake, which is a loss. That's 79 barrels per day due to gas interference. The effective stroke with the plunger opens when the valve opens is 38.7 inches, which means the pump displacement effective is 74 inches. You have to take away the free gas, which is 5 barrels, and then you have to subtract the slippage, which is 11 barrels, and that gives us a pump displacement of liquid at the pump conditions of 58 barrels per day. Then, if you want to go to the stock tank, you have to adjust for temperature and pressure to go from the pump temperature and pressure down to stock tank conditions, and that reduces this volume down to about 53 barrels per day. And this is what the input. So anyway, it's a little bit off, but I'm not sure exactly why. But it's a lot better than saying this well should produce 74 barrels a day. Now, the gas produced up the tubing is determined at the pump conditions and the pump calculations from the pump card. And when you shoot at fluid level, you also can determine the amount of gas up the casing. And that gives you the total gas produced at the tubing and casing. And that allows us to calculate the separator down separator efficiency. So here's an example, and we have 8.7 MCF of gas going up the tubing from the pump card, and 9.1 MCF of gas going up the casing, and that shows that the separation efficiency is poor, 51%. That's 9.1 MCF going up the casing over total gas produced from the well. That's 17.8. So when you look at the report in TAM on the tab that shows the summary tab, it shows that we've got this much gas dissolved in oil, this much gas goes up the tubing total, and this much gas goes up the casing. There's total gas. There's a gas that they produce from the well based on a test, which is pretty close, and it says efficiency is about 51% for the separator. So that's a valuable calculation. So this equivalent gas rate pump fillage line, it allows us to first of all, shows how much liquid is in the pump when the trailing valve opens. And it takes into account all those parameters that have an impact so that you can calculate an adjusted pump displacement that is typically going to be less than the maximum plunger travel displacement or the effective plunger travel displacement. Now this is a well, and we can look at this example later, but the production in the tank was 16 barrels a day, and this well is the representative stroke. And you can see that if we look at it, it calculates that we should be producing 198 barrels per day. And so the calculations by this much effective travel with this much gas in solution, with this delay of the trailing valve close, see it closed right there, not at the bottom of the stroke, shows a lot more liquid production. What's going on here? Well, if you overlay all 200 strokes, what you see is that in this case, there's 3 sets of strokes. Here's when you first turn it on, and then here's after it's pumped a while, and here's after it's pumped even longer, but the average is 67 inches for the average stroke. So if we look at the average stroke, then that didn't work. It still calculated too much production. But the one that matches is the one that's over here. This is how the pump runs all day long, where we got the 16 barrels per day with a 29-inch downhole pump stroke. So this pump, we should be controlling runtime. It's not full very much. Here's another well. If you look at all the strokes that we overlay, we can see that this is when the pump's full. And what's this? Well, we'll talk about that in a minute. And then so it starts to pump up, and here's typically where it normally operates, and the representative strokes around 53.7 effective plunger travel. And so that's the effective travel. But again, it says 56 barrels a day versus 20, what we measured. What's going on here? And this is the example called runtime. And so if we look at the full card, which is right here, and look at the pumped off card, which is right here, we see this much additional downhole stroke when the pump's not full. Well, why is there this much additional downhole stroke? Well, because the plunger velocity is a lot faster right here, and the faster the plunger velocity on the downstroke is, the more downhole stroke you have. So this over travel when the pump's not full is typical that you would see occur when the pumps has incomplete pump fillage because of velocity profile changes, and it can in some cases create a pump off tag and cause damage when the pump's not full. I've seen that on several different wells. So in this case, we went in and changed the runtime to 12 hours, and now when we change it to 12 hours, the adjusted pump displacement with 24 hours is too much, and then we adjust it to 12, we get much closer to the 20 barrels per day versus 28 barrels per day. So by adjusting the runtime in this case, along with selecting the representative stroke, we can get very close to the actual production in the tank But if we didn't make the adjustment for runtime, we'd be way off. This just shows the slippage calculator, and this is a well that shows 159 barrels per day slippage, 160 barrels per day. And this is an example we have, again, an examples file. And this is an example that helped show the impact on the shape of the pump card when there's quite a bit of slippage. And so here is the calculation from this spreadsheet you have, and it shows all the different clearances, or let's see what this is. This is different plunger sizes, and here's the clearances on the bottom, and here's the slippage calculation. And if you have a pump clearance around 5 inches per day, you get about 60 barrels a day slippage. But they actually ran in the well a 9,000 clearance, and they were getting 160 barrels a day. And the operator called and said, "What's wrong with my pump?" Because he didn't realize that he was getting 160 barrels a day slippage. And so what should you do? Well, what you should do is that you should use QROD, so which predictive program assume the pump has 100% pump fillage, and use this calculator in QROD, and then select the amount of slippage that you want based on your design. And so here is QROD, and here's the input for QROD, and you click on the calculator button next to pump efficiency, and this screen pops open, and you can enter in the you can enter in the pump clearances, the viscosity, and this is defaulted, and the plunger length. And then when you say calculate, at the same target speed you're going to operate the well at, it'll calculate a surface dynamometer card that says, well, this is 650 barrels per day. And if you use a pump clearance of 9 thousandths, then you're going to have a pump efficiency of 75%. And you may say, well, that's too much losses. 25% of my production is too much losses. But you may say that's satisfactory if you have solids produced. And so there's your actual production. It's going to be much less than your expected production with a pump full liquid. Now, so here is the pump pumping 651 barrels a day in QROD, and here's your adjusted pump's displacement based on slippage, and here's your volumetric efficiency, 75%, and there's your predicted surface card and pump card that's anchored and full of liquid. And that's the condition we're talking about right here. Now this is the report in QROD that once you have these inputs put in, and you can see here that if you pick 9 thousandths, you're getting about 160, 155, 156, 159 barrels per day slippage for the Patterson slippage equation. So that's the part that people often overlook, and that's why this design program in QROD is important, because it allows you to design your pump clearances before you run it in the well, you're pumping the well. So this is the well, and this pump is, the tubing is anchored, and this shape that looks like this shape here on the sides, it's anchored, it's not unanchored. Why do I know? Because I told the operator it might be unanchored. He went out and checked it, and no, it's anchored, he said. And we were using a default we weren't using any slippage calculator at all. And he said, "What's wrong?" I said, "Well, what's your pump clearance?" And he said he didn't know. And so after about 2 weeks of searching, he found the pump clearance was 9 thousandths. And based on 9 thousandths, you get a pump slippage of about 155 barrels per day, and some loss of gas in solution. And so that results in an efficiency of about 70 to 75%. So the problem wasn't that the pump wasn't pumping what they designed. The problem was that they didn't understand that the effective plunger travel when the pump's full liquid wasn't 577 barrels per day, but actually 402 barrels per day, based on reduction from slippage. And so here's the calculation. We put this data inside of the TAM software, this dynamometer card, and we calculate that this is our pump displacement, and here's our adjustments that we made. And there's losses of 27, almost 28 inches of pump displacement, and that's equivalent to about 160 barrels a day. And this number here, 404, matches up very close, with the 402 that the operator measured in the tank. So again, this is an example where they could have, but they didn't. They just used the table and ran a 9 thousandths clearance in the well because of the plunger diameter, and they should have calculated with at least with QROD or the Excel spreadsheet. So, you can troubleshoot your production based on these adjustments that we make to see if what you're getting in a tank is what you should get based on your pump clearance. You can also look at the wear rate and see as the pump wears, you should see a drop in your production, and you can actually see your reduction increase in your pump clearances. You can use the design clearances for a new well to match your production from your well. That can help you. And as the pump wears, in some cases, you can increase your pumping speed and maintain a full pump and increase your run life. So some operators have done this successfully, where they run a fairly tight clearance at a slow speed to have high slippage, and as a pump wears, they increase their pumping speed and maintain a full pump as their pump wears. But by using these calculations, you should be able to know what your expected performance of every well that you have is. So we can determine this by knowing how much gas goes up the tubing to adjust the actual tubing fluid gradient. We can use our card to match what we calculate our production in the tank. The problem with this method is it takes a lot more data to make the calculations work. Sometimes the pump clearance is difficult to figure out or find out. It's often not recorded. The difference between liquid in the tank and the pump displacement compared to the effective plunger travel is now a lot easier to answer that question and explain. The reason primarily often is because of the free gas in the pump and slippage, and probably sometimes runtime. It also helps us troubleshoot wells. The equivalent gas repump filters line is a way to help us troubleshoot wells. This is a recommendation. If you're interested in more details, you ought to consider buying Dr. Podio's book on fluid levels, and they have another one on pump cards, dynamometer pumping wells, rod pump wells. All right, so that's my presentation. Are there any questions or comments?
Oh yes, we have several good questions here. Some are sent on the share chat, and some are coming to the direct chat. But yes, we do have several questions. Let's start with that. And we have a question asking for does the plunger length affect the slippage?
Yes, the plunger length. Let's say that the plunger default is 4 foot, and 4 is you'll be multiplying times the slippage by 1/4, and then if you had a 5 foot plunger, it'd be 1/5. So it goes from 25% constant to another pump would reduce it to 20%. So by 20% factor. So anyway, I guess my comment is yes, every foot increase in the pump length reduces the slippage approximately 5%. So that would be that's kind of a, but it's it's 1 over the length is the ratio.
Okay. We have more questions. Say, why different wells with the same effective plunger travel and 60% fillage? The blue line is closer in one well and farther in the other well to the effective plunger line.
Right. So it's really critical to have those valve open close points selected. And often, if you're using the TAM software, those points, you haven't clicked the annotation button, and turned on the valve open close points, and sometimes the program's not picking the points right. So the first thing you need to make sure is that select the valve open and close points, and then look at the calculated pump discharge pressure and the calculated pump intake pressure based on the height of the pump card. And those are fairly important in this whole calculation.
Okay. Jun Shu is asking, Lynn, how to determine the tubing gradient more accurately when gas in presence, when not knowing how much gas entering the pump?
Yeah. Well, that's what I thought. I thought I'm going to put the. I thought when we did this that we put the multi-phase flow method in the software, and we used the gas up the tubing to calculate the gradient based on multi-phase flow, and I thought that would really be really accurate. And so we still have some work on that, but it works really well for really high oil cut wells now, and we've gotten a lot of good matches on that. And there may be a bug we just need to look at some more, but it doesn't do very good yet for water. But we are doing that. The multi-phase flow method in TAM does a good job calculating a gradient if it's all oil, high percent oil, but does a poor job if it's high water cut. And so there's probably some kind of breakdown, but we'll fix that eventually and figure it out. But that's what we do. We use the multi-phase flow program, and the a flow between the rods, bodies, and the tubing, along with a friction factor for flow, along with the viscosity. And it looks like right now we've got some kind of small issue we need to address. But yeah, and we use a gas from the pump. Gas calculated from the pump up the tubing, so that's all being taken care of.
Okay, kind of a generic question. Some dyno cars in heavy oil field are wavy at upstroke and downstroke. Is it downhole friction or measurement error?
Okay, that's a good question. When you have a wavy pump card on the upstroke and downstroke, in viscous crude, normally it's due to several things. If you have a really big plunger and it's a shallow well, and the big plunger causes the discharge pressure in the plunger to increase during the upstroke because of restricted flow out of the pump in the tubing, that can cause a bottled up pump increase in load, and then it will echo up and down the tubing and make a wavy pump card. So that peak load is impacted by bottled up pumps in shallow wells, and you'll see a wavy line, and that's a pressure force caused by a large diameter pump and a shallow well. Most of the wells that we see in this area are typically not that shallow. They're deeper than 3,000 feet, and we usually don't see the wavy character on our pump cards in this area. We usually just see one hump because it takes more. It's not wavy. Now, the other thing that can cause it to be wavy is if you have your rod string upside down. When you type the rod string into TAM, if the rod string's upside down, it makes the pump card wavy. If the rod string's entered in incorrectly, it makes the wave equation models the behavior of the rod string. And so if the rod string that it models isn't what's in the well, then that'll make the pump card wavy. So the first thing I usually check is this rod string entered in, is it input correctly? So those are the two reasons for it to be wavy, but it could be wavy if the fluids are surging away from the pump, which is I think is unlikely. So in most cases, the discharge pressure and intake pressure are constant. And so the idea of a flat line on the upstroke and downstroke of the pump card mean that the pump intake, there's no change in load acting across the plunger. And possibly in a few wells in the world, there may be the pressure across the pump may not be constant during the upstroke or during the downstroke, and that could cause a changing load. Like the bottled up pump, the pressure goes way up, and then it appears to drop off after the flow begins. Okay.
Well, putting aside that low probably option is we have then a shallow well with big plunger, so we have fluid inertia involved in there. And the second option that you mentioned was having a run input on the sucker rod string. And I could have a third one that is not actually necessarily for heavy oil, but also some hydraulic pumping units that are not in good balance can create a really wavy upstroke and downstroke dyno cars.
Right. Well, the heavy oil doesn't behave the same. So I've got data from a lot of wells in Venezuela, probably over 100. And those wells were around 8,000 foot deep. And those wells just have, see, the viscous fluid causes more dampening on the rod. So if the pump card is, we talked about this on the second Ask Echometer, when the pump card is concave outward, like a bowl, then you can increase your damping factor and flatten the pump card out. And that's fluid friction. So fluid friction is a problem in the wells in Venezuela, that the fluid friction is 5 or 10 times sometimes what we'd normally see in the U.S. So that's the low damping factor. But on a shallow well with a large diameter pump, that's what makes the hump. It's double hump. So you get a big hump to pick up cause the fluid to leave the pump chamber, and then an echo hump, and that's two hump. But most of the time, that just occurs on a very shallow well with a diameter of the plunger larger than the flow area in the tubing. So the viscous crude just means you need to have higher damping factor.
Right. I have another question, probably with quick answer. Is a pump clearance of one side, for example, heavy oil in Kuwait uses 10 thousandths of an inch, so clearance equation is 0.01, right? The answer would be
right. So if you have 10 thousandths in Kuwait, then it's 0.01 for the pump clearance. So that's the OD of the plunger subtracted from the ID of the barrel. And so for Kuwait, their wells are very shallow, and they're very viscous 10 API gravity crude. And in a lot of cases, their temperature is changing because they're trying to do a thermal flood, and so they're trying to heat the oil up, and that drops the viscosity. But if they don't maintain the heat, then the temperature of the earth cools off back to normal temperature, and the oil becomes much more viscous. So it's an issue of not just the gravity of the crude, but it's also an issue about the temperature. So the temperature can also cause a problem.
Yes, and I would like to clarify that it's asking, is the pump clearance of one side? And I would say, well, the pump clearance is actually the difference in diameter between the ID of the barrel and the OD of the plunger.
That's right. That's right.
You should consider as an OD, no one side of that diameter, but just the difference in diameter between.
Right. So it's actually,
barrel.
If it was centered, it'd be half the clearance, but we don't calculate that way. Like Gustavo said, it's the OD of the barrel minus the ID of the plunger. Yeah, but it's centered, so it's so clearance is really, that's the total clearance, not the average clearance between the plunger and the barrel.
Okay, a question related to slides 15 and 17, which is the same dyno car. Aaron Walsh is asking, what drives the position of the gas-free fillage point relative to the traveling valve open point? For example, why is there a gap between the black and the blue line in those slides 15 and 17?
Let's go on a little farther. This explains this. This is the same thing. And so when you start at the intake pressure and the pump fills up with liquid and gas, it fills up with this much liquid and this much gas at the pump intake pressure of 242 psi. So there's gas inside the pump, inside this pump, and there's liquid. And if you could separate it all out, there would be 41 inches of liquid, and then at the very top of the stroke, when the slippage has occurred, then you'd have this much liquid and then this much gas. Now, when the plunger moves down this way, and the pressure increases as this load drops. So as a plunger moves down, the load on the rods is increasing, and the pump load acting on the bottom of the rods is decreasing. And at this point right here, we have increased the pressure inside the pump chamber to the discharge pressure, and the gas volume now, the volume times the pressure, is 2.77 inches versus 41 inches at the intake pressure. So back to this equation right here. Pressure times volume over the Z factor equals pressure times volume at the discharge over the Z factor. If we just ignore the Z factor, we can just say pressure times volume equals pressure times volume intake at just equals discharge. So if you were to take 2.77 times 2500 should be equal to 41.35 times 242, about pretty close without the effect of the Z factor. And so that's all that's what compression is. You take 41 inches of gas at 242 psi pressure of low pressure, big volume, and you compress it to a high pressure, which is 2,587 psi, to a small volume, 2.77 inches, because the cross-sectional areas are equal in both cases. The area of the plunger didn't change. So is that the question?
I hope.
Yeah, I hope so too.
Okay,
I
Gary's
hope so
asking,
too.
what considerations, if any, should one make if there is a measure at sand being produced in the well?
Oh, that's a hard question because I don't really know the answer to that question. I usually think of sand as just solids that take up space, just like oil. And usually the sand is carried by the oil, maybe by the water. But if you're making a large amount of sand, there's two problems. One problem is the sand causes pump sticking, and that may be why you're opening your clearances up to prevent scoring of the barrel. But the other thing you're suggesting, which is true, is that if you produce 5% sand, then that means your liquid volume is actually 5% larger, and sand's taking up some of that space. So I think you should probably consider the sand volume as part of the liquid volume if you're putting in your liquid. That doesn't affect the calculations. It's just going to have sand is going to be part of the calculation at the pump. So we should be so let's say you make 5% sand, then the liquid volume you calculate at the pump, adjusted for stock tank conditions, should still be 5% too high because there should be still some sand volume that was inside the pump and it was assumed to be liquid, but it wasn't. So it really won't make much difference other than we're going to calculate too large a volume because the sand also is part of the volume.
Okay, we have a question that's kind of related to this topic, but we didn't fully cover. And the question is, what is the precision of calculating the pump intake pressure with the dynamometer, and what are the most important variables to consider? Okay,
that's a good question. So if we go look at this slide right here, this is slide 19. And this line right here is called, this dashed line in black is called the fluid load line from the fluid level. And it is calculating what the expected pump load is based on the intake pressure, subtract from the discharge pressure times area of the pump. And so if the pump card load line, the pump card from the wave equation matches up with that line, then the calculations are pretty close. It's a good match. So when you ask what's the precision, the first thing I do when I look at the pump card is I look at the load line from the fluid level shot, called FO from the fluid level, and the pump card. If those two load lines aren't close, then I start wondering what input data is not correct. And I got to go check my plunger size. I got to go check my tubing fluid gradient. I have to check my true vertical pump depth. So tubing pressure. So if we go back to that equation, let me find that equation right here. Where's it at? It's probably before this. So there's the equation is shown right here. This is the equation. So tubing pressure is important. The deviation survey and the pump depth is important. And the gradient of the fluid inside the tubing is important for the discharge pressure. And that means the production rate, oil and water need to be typed in and maybe lightened if there's gas going up the tubing. And then the height of the pump card, FO up minus FO down. The program assumes the average load and the upstroke and the zero load line for the pump card. And the plunger area, any one of those parameters could be wrong. And that would make the pump intake pressure calculation right there not match the pump card. And so we're trying to match this red line and the pump card load line. And you can argue that, well, it's not quite right. Maybe that's the pump intake pressure and this is mechanical friction. So then I'd say, well, this is mechanical friction here, and so I'd lower that line down to here. I guess my point is that you can look at the pump card and see this load line right here. It should be fairly flat, and it should match up fairly close to the load line calculated from fluid level shot. And that's what we're showing right here. That's a good match. That means that most of these parameters are pretty close. That means the precision is good. Okay, and the most important thing to consider, well, geez, if the plunger size is wrong, then this is way off. So the plunger diameter is important. The tubing fluid gradient, if it's really gassy, it could be way off. So you have to make an adjustment sometimes to the tubing fluid gradient, and don't use the gas rate tubing fluid gradient in TAM, this one right here, if you got a lot of gas going up the tubing. And so in this case right here, I didn't use a default 0.365 tubing fluid gradient of oil because I thought that this meant there's gas in the oil going up the tubing, and that's going to make the gradient less. And so that's why right here I put in a lower tubing fluid gradient. And so the most important variables, any one of these variables right here can have a big impact. If you have back pressure on your well, you need to put the back pressure in and not let the program default to 0 or 50 psi tubing pressure. So you need to know the tubing pressure, true vertical pump depth, that means the pump depth should be correct, and the deviation survey should be input. You need to know the tubing fluid gradient. How close? I don't know. It makes a little bit of difference. The height of the pump card comes from right here, and that you can adjust that. The plunger area, sometimes there's a change in the well, and you forget to change the plunger diameter, and that makes the red line way off from the pump card. And so it's not unusual for us to see once a week someone has a problem, and it's because the plunger area is not entered in correctly. So probably the plunger area is the most critical variable to consider.
Okay. Well, the next question is that kind of question that contributes with our long list of improvement for the TAM software. And the question is, fluid viscosity is 0.75 centipoa by default in the software. But although I type a low API gravity like 11.5 in fluid properties, the software omits this condition. Should the software show an alert, in this case, telling me that I must change the fluid viscosity?
Right. That's a good question because, this is software. And originally, when we first did the testing, 0.76 worked pretty well for a lot of wells in the Permian Basin. And I wasn't that worried about changing the viscosity. And then we started doing testing up in Wyoming. We started seeing a bigger impact because we're starting to see lower API gravity crude. And so when we first programmed it, we didn't really know what to do because we didn't have enough experience with all kinds of crudes. And that's where that spreadsheet came from. The spreadsheet came out of us trying to figure out how to fix the problem we were seeing. And so for right now, Echometer is providing you an Excel spreadsheet, and you can type in a different viscosity based on the spreadsheet. And that will provide a better match. And if you find something that's different than what we said in the spreadsheet, then let us know and send us data, and we'll try to make those adjustments to the program. And sometime in the future, we'll make this correction. So this is a correction we've been working on since 2012. So this is something that we've been working on for 8 years trying to figure out. We've done several presentations on it, and we've asked for data from customers, and we're getting closer to the right answer. So right now, the right answer is use the spreadsheet that we provide, and you type in the number based on your well conditions for 0.76.
There's another question, and I think it's related to the Patterson equation for slippage calculation. And the question is, what is the maximum viscosity that this calculation can still be applicable?
I don't know. I don't know if there's maximum viscosity because it's a more complicated problem than this equation. And so we've done some work with Sheldon Wang with Midwestern to solve the Bernoulli equation. And so long term we may have to use the Bernoulli equation when we start to have unusual conditions. But for a lot of oil field conditions, this works really well for a stroke. But it's averaged over the entire stroke, is how we measure the data. And whereas a Bernoulli equation would calculate over each section, when you're picking up the fluid load, carrying the fluid load, compressing the fluids, it would handle all those conditions. And so, long term, we may end up using the Bernoulli equation, but right now this equation works great, and we don't really know the limitations on the viscosity. So I would say that you have wells, Echometer have wells, and so when you encounter something that doesn't work, it would be wonderful if you would provide us feedback so that we could include what you determine in future enhancements of the software. So we always welcome any kind of feedback. If you find that your oil that has a viscosity of 1,000 just doesn't work, then maybe that would indicate that there's no slippage, and as long as the pump clearances are less than 0.02 or point something, I don't know what they would be, but there may be some limitations, and I don't know those limitations yet. I'm more familiar with the wells from West Texas that don't have viscous crude.
Yeah, it's probably good to remind the user that a good part of the software improvements are based on their questions, but also based on their feedback and their information.
Yeah, yes, I think any kind of feedback would be great.
Yeah. Okay. Aaron is asking, what else would you look at if you were happy with the estimates of slippage and gas losses, but you still had some unexplained difference between expected and actual production? And the first thing that comes to my mind was to write back and say, look for a hole in tubing, but we'll have a better answer.
Probably what I'd say is probably pump wear. So if you're having if you think the calculations have been matching well and you start to see a well where they're not matching, then I would start to expect some kind of pump wear problem. And that's what we kind of talked about in the conclusion slides, is that you can use this because it's based on a new pump. And we've seen some wells where in fact, in the field in Wyoming, the operator would use the slippage equation because they had a certain rate of wear based on the sand they produced, and they knew that as they produce a well, over time they would get more slippage because the sand would start to wear the pump, and then they would increase the speed. So probably the number one thing that we don't know about is the pump wear. So that would be my comment on that question.
I have a question from Daniel. Is in the edit window we input a fluid viscosity, but he's asking, it's a standard condition. Is it surface or bottom hole temperature?
Right. So let's go find that calculation. All right. So this is a table in the spreadsheet, and so the spreadsheet that we provide has this table calculated based on what you input. And so this is you type in the oil and the water production rates, and the oil and the water gravity, and the bubble point pressure, and then the temperature, and the temperature is the temperature at the pump, because this is the downhole temperature viscosity calculations. And so if we go back to this table, all these viscosities here in this column for the gas and the water and the oil, and the gas viscosity is not using the calculation, it's just the oil and the water viscosity. These are at the reservoir temperature, and these are the intake pressures, okay? And so the bubble point pressure is how much gas goes in solution. So in the spreadsheet, it says bubble point pressure, and you type in the pump intake pressure, because the pump intake pressure is what limits the amount of free gas in solution. We're going to assume that all gas is free. So use the formation temperature at the pump. Use the pump intake pressure for the bubble point pressure, and then the calculations show you the viscosity average, and so you use this viscosity average if you're above 30 of the oil, if you're below 30 degrees API, and then you use the combination viscosity if you have a light oil above 30 degrees API. So there's a huge difference between the viscosity here of the mixture versus the viscosity of the oil. And so this means that the pump doesn't leak if you have heavy crude, and the pump really leaks if it's water. That's kind of what that shows. Okay, so that's kind of the answer to this question. You use reservoir temperature at the pump and use intake pressure for your bubble point pressure to determine gas in solution.
So Lynn, I put out there on our website, if you go to our Ask Echometer webpage and then scroll down to today's session, session 6, and along with the TAM data sets, I also have the 2 calculator spreadsheets and then also the 2 papers that you referenced. So all of that's in a folder that they can download. Yep,
Okay,
so
here's this right here, and then
so download TAM example files.
So those spreadsheets are in this example right here.
Along with the 2 papers.
Okay, great. Those are great questions.
Okay, so now you can jump into the last question from Bert. That's yes, slide number 50.
You're asking about this little bounce right there and this little bounce right there. When there's quite a bit of clearance, the plunger moves, and then due to the harmonics of the rod string, it pauses, and that's what this is the frequency of this little bounce is due to the frequency of the rod string. So what I mean by that is it takes a certain amount of time for the force to travel through the rod string, and so when you start to pick up the pump load, this much time from here to here. This isn't time, but there is time, and we'll look at that in a minute. As an example, it takes this much time for the wave to travel up and down the rod string, and so what we first thought when we first saw this, we thought this was an anchor tubing, and it's not. This is not an anchor tubing. This is slippage, and so it slips here, and the pump pauses because of harmonics, and it slips a lot more there, and then there it picks up the rest of the load. And so this is a typical shape on the left and the right side of the pump card when you have slippage in an anchored tubing. So this is anchored tubing, but 9,000 pump clearance, and I've seen this on quite a few wells, and it's due to the rod harmonic, the depth of the well, and we'll look at it as a first example. But that's a great question. This was an argument that Sam Gibbs and Ken Null and I had a lot, because at first I thought this was being indicated unanchored tubing, and Sam and Ken said no, this is just slippage. And after I saw this data on this well, I said, hey, this well is anchored because the operator actually pulled tension on the tubing, and this is only slippage. And when I agreed with Sam and Ken about this, they said no, the test well at Texas Tech is unanchored, and I said no, it's anchored because that slope is just due to slippage. And so this is a complicated shape here, and it shows up when you have large clearances and anchored tubing, and this is a motion. So the plunger moves, and the harmonic causes the pause, and the slippage causes the load to start to drop off, and then the harmonic causes it to move again, and that's what that is. And that's a super observant question from Bert Pond. So most people don't see that.
So we'll have one more question. asking, when having a heavy oil, we frequently have non-accounted friction that makes the downhole car look bigger or taller than what it really is. Will this affect the gas-free line calculation?
So the question is, what's the fluid? You're asking what's the fluid load? If the red line called FO up the doesn't match the pump card, then there's something that you need to look at. And so anytime you're looking at the FO up line compared to, I'm going to go back to slide 15 real quick. All right, so here's slide 15, and your question is, if this is all bowed out because of friction due to viscous crude, then and the program picks the average load, then it's going to calculate the wrong pump intake pressure because of the too low damping factor. So as you increase the damping factor, this line should become flat if it's not mechanical friction. So you need to look at this line if it's not flat and you have extra friction in your well due to viscous crude, then you need to increase the damping factor, because the damping factor increasing will correct for the viscous friction. But the damping factor increasing will not correct for mechanical friction, which is due to mechanical contact. This load line being flat represents a constant differential pressure across the pump. If the pump card is concave outward, that just means that you haven't accounted for the excessive damping from fluid on the rod string. The damping factor should be increased. But damping factors don't fix mechanical friction. And that's all discussed in the second presentation we did on forces not accounted for by the wave equation on Ask Echometer. So if you're curious about this question about mechanical friction, damping factors, please review that Ask Echometer presentation and feel free to email us questions about that. So Gustavo, do we have any more questions to cover?
We have one last comment from Tariq. Is having say, I got a perfect textbook pump car, an anchored tubing. The fluid level is at 2,800 feet. The pump is at 3,200. Shooting nipple 4,000. I'm not sure about it, but no fluid coming out of the bleed valve to take a build up. Is there a possibility for a tubing leak or something else?
Yes, most likely it's either the casing check valve or a tubing leak. And so you should be able to, you should isolate the casing and see if your pump should pressure up the tubing. So it's a pretty quick check is just to close off the valves at the surface and don't do many strokes. If it's a leaky check at the surface, it's going to let fluid leak back down the casing. Then when you close it off, the pressure is going to go up really fast, and you've identified you have a bad check where the check could be installed backwards, or it could be now, another thing you can do is there's a paper on troubleshooting rod pump wells by shooting down the tubing. You can shoot down the tubing and see if you have a liquid level not at the surface, and that would maybe indicate you're pumping the liquid out of hole. So there's some things you can do. Download that paper off our webpage. It's called Troubleshooting Rod Pump Wells with Acoustic Instrument, and it's a paper that John Sparks and I wrote, along with Joe Norman pressure testing the tubing with a wireless pressure transducer. Those both are good papers for reference on that question. But sure, that could be a problem. Either bad casing check valve likely, or a hole in the tubing likely, and you should be able to pressure up the tube at the pump. And now I've seen, another thing that can happen is that if you have a fiber pump, if the pump has fibers, not a metal seal, then if you have enough differential pressure that the slippage can be so high that it can't produce any fluid anymore. So that usually occurs when you run it's called sometimes they call it a Pampa pump, but it's a fiber pump that has a fiber plunger that it doesn't have high pressure seal, and the deeper you get, the more it leaks, and so you have to watch out for that too. So it could be one of those three things, probably a hole in the tubing near the surface.
One last question, Lynn, is on the slide number 10. I got someone asking if the time for the gas to go into a solution should not be the time for one stroke, which is about 8 seconds.
Which is this slide right here. So there's slide number 10. And the question is, you said 8 seconds. So if we go across if you go across on 8 seconds, then that would be like a 40, like a 40-degree API oil. And
no,
so
they are considering that if they should consider the time for the gas to go into solution, it should be the time for a whole stroke. So one stroke will last about 8 seconds.
Let's go to an example and show that, okay? So let's go to an example, and let's pick the really gassy well first. And this is from last week, Carrie Ann's presentations. And so now we've got session 6, and I call that liquid pumps. And so that you open that one up, and this is the well, gas interference. And so the question is, and let me turn on the annotation for FO from the fluid level. So I'm going to go in here and turn on FO from the fluid level right there. Annotation, and so I just picked pump card annotations. And so now we've got that line right there, and the line matches up pretty well. And the question is, how long is this? How many seconds is this stroke? And so this stroke is, let's go to details view. I think I can change it here. So if I go to strokes per minute, I can click on this and change it to seconds. And so this whole stroke is 7 seconds. And so, okay, 7 seconds. Well, what is the pressure on the fluid from here to here? Well, the pressure from here to here is the intake pressure. And here it goes from intake pressure to discharge pressure. And the trailing valve opens, and then the pressure doesn't change. So the question is, so back on that slide, let me slip back to that slide. This slide means that the oil and gas are in contact and being mixed at a certain pressure. And so, and it takes about 8 seconds for 40 degree API crude to have the gas go in solution. And okay, how long is this from here to here? Because this is what we're talking about, this curve right here. So we have an analysis plot that shows that. So if you go to the analysis plot, and you come with your line, and you come, let's look at, I think we can plot chamber pressure. Let's see if we can. Chamber pressure. So there's a plot of chamber pressure, and notice here that when we get to right there, when the right there is where the standing valve opens, and well fluids start to enter the pump chamber, and so from here to here, the chamber pressure is at intake pressure. So the fluid's at intake pressure. Okay, and it's filling the pump, and then we're starting to compress, but look, we're still at low pressure. Okay, and let's turn it from clock time to seconds. Okay, from this point to that point, how long is it? Well, from that point to that point, that time is 4.35 seconds, and that time right there is 4.35 to, that's 1 second from here to here, and that means that the oil is being compressed for 1 second, and it's not at the discharge pressure. It's at an average, not even average. It's at a pressure probably lower than the average of the intake pressure plus discharge pressure in the compression cycle. So maybe you'd say it's at the discharge pressure completely mixed for less than a half a second. And if you go back to this chart, it says you have to have 8 seconds of contact to push all the gas in solution. So my argument is this time is short, and it's not in contact for enough time to push very much, if any, gas back in solution. Plus, I'm claiming that, dang, these wells produce water, and the water is separating the oil and the gas. So that's a question, right?
Yes, then you
Okay.
shouldn't consider one stroke time instead of
No,
HA,
you
consider
can't
the time
consider
for the compression. Yeah.
Yeah, you can't consider one stroke time because the compression occurs right here, and it's a short time, maybe less than a second, normally.
I don't know if you want to quickly show something,
Yeah, well,
but
we can. I guess we probably ought to look at a few examples because we've only got about 15 more minutes before it's time to quit.
Mhm.
And so I want to show just a few examples. And so I want to go pick a well. Well, first of all, this when I go to the Details tab, I want you to notice that this line right here is positioned on this pump card based on what? Based on that point and that point and the compression and the amount of liquid inside the pump chamber. And so if I go to a different stroke, those points, they move. And so this equivalent gas rate pump fillage line moves on every stroke based on where this point is, that point is, and the average of the loads, unless you go in and go into pump card analysis and look at the pump intake pressure and see how this line will change. Right now it says that load line is 4,519 pounds. If I go to another stroke, it's going to be different, 4,620 pounds. So it changes, and all those changes have an impact. So the pump intake pressure changed to 670 there. If I go back to that stroke, it's going to change to 696. And so all those, the pressure, pump intake pressure, pump discharge pressure, all that is calculated based on the pump card. And it can change from stroke to stroke because the trailing valve doesn't always open at exactly the same point. And so that when it opens, that's when the pressure inside the pump chamber is the discharge pressure. When at top of stroke, we assume that's when we have the intake pressure, and that's the compression curve right there. So normally when we open up this pump card analysis button right here, when we click on that button right there and open it, then you should start at the first and make sure the damping factors are reasonable. Do you have any mechanical friction you want to include at the surface? Do you want to, I'm going to skip the D-ramp and valve open close points. Tubing fluid gradient, you need to make sure what method you want to use. And here I entered a lower tubing fluid gradient because there's a lot of gas going up the tubing. It's a lot lower than the gas-free gradient. 0.413 is a gas-free gradient. It's lower than that. And so the multi-phase flow program, the software didn't calculate a very good one. And we need to work on fixing this if it's a bug, fixing this, or at least selecting a different method. Like maybe we'd go to Duns and Ross or go to Hagedorn and Brown, but right now we're using um, Duns and Gray. Duns and Gray is the method we're using right now. All right, so Ross Gray method, not Duns. Ross Gray is the method we use right here. And then the pump intake pressure is calculated based on the fluid load line average up and the fluid load line average down. And that's where this pump intake pressure comes from. The discharge pressure comes from the tubing gradient tab right here. So we've got the tubing fluid gradient, and then we can calculate the discharge pressure. And then it goes through on the last tab where the pump displacement is calculated. And we've already talked about how this is calculated. And this is where we adjust for stock tank. Okay, and then we have an adjustment for runtime. Well, in this well, the runtime is 100%. So if we go into Edit and we click on the Prime Mover tab, so if we go to here and we click on List System, we click on Prime Mover, it's running 100%. So there's no adjustment for runtime in this well because it's on hand. It runs 100% of the time. So now that's this example. This is a great example to look at tubing fluid gradients. It's got a really high gassy fluid level, a gas compression curve. This is an example I've had for a long time. It's really a good example. If I pick another well, let's look at what other wells we have. We have several other wells. This is a well that was that the operator was aggravated that the well only made 402 barrels a day. And he called and said, why does my well only make, if we go to the dyno data and we look at the details view, it says, well, this card would calculate 420 barrels a day. but the field view says 580. So he said, why isn't my pump making 580? Well, the answer was, in this case, because of slippage, okay, and a little bit of gas. So that's why this one, this is a good example because it has, if we go to click on edit, and then we click on the lift system and the rod string, down here, this well had a 9 thousandths pump clearance and a 2 1/4 pump. And so the operator ran the 9 thousandths pump clearance because the 2007 paper said if you're in the Permian Basin and you're less than 8,000 feet and you run a 2 1/4 pump, run a 9 thousandths pump clearance. And they did that, and it was a lot leakier than they expected. So this is an example where the operator said, what's wrong with my pump? Well, what's wrong with his pump is he didn't use the slippage calculator to calculate the amount of slippage and then design his well based on additional 160 barrels a day slippage. So this is a good example, and it shows that bounce. And so if we go to the analysis plots and we look at this in terms of time, let's look at this in terms of time, and let's look at not plunger velocity here, but polish rod load. And so we see a peak there and another peak there. That's probably about the frequency of the rod string, that time. And that time is what? That time from here to here. So that is 3.9 seconds minus about 2 seconds. That's almost about 2 seconds. So if we plot this pump card in terms of time, elapsed time, which is time in seconds, this time right here is 1 second. So that's about half. That's half the time for the stroke. So that's a one-way travel of the harmonic, and that's what that's where the plunger velocity kind of pauses. And if we look at the plunger velocity right here, let's go to plunger velocity. We'll see, I think, hopefully I won't be wrong here, that the plunger velocity, well, it's not moving. It's zero, and it pauses there, and that's what causes that load to leak back off. And then when it starts to move again, we see the load pick back up. And so this is pump load and plunger velocity. So that's what that you'll see this a lot on anchored tubing with anchored tubing with open clearances. So you'll see that little bump there, this little bump right here, that little bump and that little bump there. That's large pump, open clearances. Is about an 8,000 foot deep well, and you see that little bounce. The next one is, let's see what else we have. Delayed closing trailing valves. Let me talk about the delayed closing trailing valve just real quick, because it can be different. It can be different ways. The plunge, and so this well is pounding fluid. It's got a low pump intake pressure, and there's the pound. But this right here is the delay, and so from here to here, you're losing about what is that? About 2 inches of stroke. And so if you don't shift this point and move the trailing valve closed to that point right there, and you go to the pump card analysis and you look at the pump calculations here, see it says the trailing valve closed delay is about 2 inches, and that's equivalent to about 5 barrels of production lost. And so that's what that represents. So every stroke in this well, let's make sure I'm right. Go to field view and go to events and show the events, and I'll go to the very last card, the 108th card, and I'll go to the very I'll go till they start to pound fluid. Go to right about here and hold down the shift key and click that, and see how they all kind of show the same delay, about the same 2 inches on all those cards. So for some reason in this well, it has a bounce at the bottom of the stroke. But if you go more to the full cards, you won't see it. So if we go over here, you don't see that. So it has to do with incomplete pump fillage. It has to probably do with probably the speed change of the plunger. But here these strokes don't show that bounce. Sometimes that often can occur depending on how the pump fillage occurs also. Those reflected waves can cause you problems on your pump card. And then the next one, we talked about free gas in the pump. Well, that's the one that we use all the examples in all the examples. And so this example of free gas in the pump is so here's our example, and here's this FO from the fluid level, and we can argue about friction. Someone might say, well, that's friction, and that's friction right there. So what we could do is we could go into the pump card analysis, and we could come to this screen right here, pump intake pressure, and notice if I pull this down and make the pump card not as tall, it means there's more gas going up the tubing. Because what happens, look, the pump intake pressure, as I move the FO up down to that line right there, it's going to cause the pump intake pressure to get higher pump intake pressure, less fluid load. Or I could say move this line right here down a little bit, right about there, and then move that line down right there, and it's about the same then. So we looked at about 300 pump cards that had incomplete pump fillage, and we found that the very best method to determine FO up and FO down for our data was to use the zero load line for FO down and the average load on the upstroke. It doesn't always work, but it's usually doesn't work usually because of mechanical friction. But in these cases, it worked okay. But this is the best option. The best defaults are average load line and the zero load line. Average load line on the upstroke and the zero load line on the downstroke. What else do we have here real quick? Well, I talked about runtime with another example. This one actually has runtime. The representative stroke is sort of an interesting concept because when you look at this data here, you've come to this well and you've collected 200 strokes. And if you look at all the strokes, let's go look at all the strokes real quick. So the strokes change, and so the very first strokes aren't full, and then there's some fuller strokes toward the end. And if you overlay all the strokes, you can see that the strokes have different amounts of pump fillage. And for this well, I would have thought that this stroke was that representative stroke because at the end of 201 strokes, those are the strokes we're seeing right there. See how the green line shows up? You just kind of run your mouse over them, and all those strokes after running for 201 strokes are out here. So if I was just going to eyeball it and pick it, I would have picked that stroke as representative. But to make the calculations match up, to get the right production to match 12 barrels of oil and 4 barrels of water, to get that matched up, we had to pick one of these strokes right here that only had a not very much downhole stroke. So that meant that if they run 24 hours a day, then this is the stroke that's running probably cutting all kinds of holes in their tubing because of gas compression. But this is a stroke that tends to make a match on 16 barrels a day. If we go over to the details tab, well, that's 5 barrels. Let's see, move a little more that way. There's close, 14 versus 16. But anyway, it's not a very full pump card, and the pump intake pressure is low, and this well has a lot of gas. They need to run a down gas separator in this well to get the gas out of the pump, and they probably would increase production. All right, Carrie Ann, I think that's probably close to 2 hours. Probably time for me to quit.
All right. Well, this has been a great session. I was looking at all of the chat and the questions and answers, and we're going to create a document with all of the questions that we received in chat, and then go ahead and get the responses written in a document so that you guys can download that. I'll have that on our website tomorrow, along with the recorded video that will have a link to access that on YouTube. So we sure appreciate you guys joining us today. It's always a pleasure having these sessions with you guys. And if you have any follow-up questions, please let us know. You can just respond to the invitation email if that's easier for you. And next week's session will be shooting fluid levels and troubleshooting gas wells. So if you're already on my registration list, you'll automatically receive a link to next week's session. We appreciate your time so much today. We're so glad that you joined us, and we look forward to seeing you all again next Wednesday. Thank you so much, and have a great week.
See you guys. Thank you very much.
Thank you, everyone.